In the last video, we talked about linear regression. Now here we're going to take a look at other types of regression as well. And you can see, in addition to linear, we have logarithmic, exponential, power, and quadratic. And you can see the equation, or the form that each equation follows for each of these, and you can also see the shape that each of these different types of regression follow. Now, one thing I want to point out is exponential and power look very similar. The only thing is that power is going to grow more gradually than your exponential. Okay, so take a look at the examples on the bottom of this page and see if you can determine which type of regression is being shown in each of them. All right, so I'll give you a minute to do that. Okay, so with the first one, I hope you guys picked logarithmic, because you could see what's happening here is it's growing more quickly at first, and then it's kind of leveling off, kind of like the logarithmic shows us above right here. Okay, it's going faster at first and then leveling off. Okay, number 2 displays linear, like what we saw in the last video. Okay, this right here shows a negative correlation. So I'm going to do some of the examples with you in this video, but not all of them. Some of them I'm going to leave for you to try on your own. All right, so we're going to skip 3. Let's take a look at number 4. Okay, I'm just going to move this over so I have some room to write. It says, in the year 2005, Jean invested $380 in stocks. Over the next 5 years, the value of her investment grew as shown in the accompanying table. So the X column shows the years since the investment, so I guess the years since 2005, and the Y column shows the value of the stock in dollars. Okay, so letter A says to write the exponential regression equation for this set of data rounding all values to 2 decimal places. All right, so we're going to do this very similar to how we did linear regression. We're going to start off by, in our calculator, we're going to plug all of the values from the first column into L1 and all of the values from the second column into L2. So you can just kind of hit pause and take a minute to do that. Okay, so now this time when you hit the stat button and you go over to calc, instead of scrolling down to number 4 for linear regression, you're going to keep scrolling down until you get to the 0 for exponential regression. You could hit enter on that, and then if you look at the second screen here, this is what you should be seeing. Okay, it looks very similar to what we see when we do the linear regression, so you could hit enter on calculate, and when you do, we're now going to see this screen right here on the bottom, and we can see an exponential regression is in the form y equals a times b to the x power. So we're going to write our equation simply like that by plugging in this a for a and this value of b for the b. Okay, so it asks us to round to 2 decimal places. So we can write, let's see, part A. We can write y equals, for our a we're going to plug in 379, and then to 2 decimal places, that'll be 0.92 times, so I'll put a parenthesis, b, which is 1.04 when we round it, to the x power. So that's the equation we get for part A. Now part B says, using this equation, find the value of her stock to the nearest dollar 10 years after her initial purchase. So what they're looking for us to do is replace the x with a 10, because the x represents the years since her investment. So we'll write y equals 379.92 times 1.04 to the 10th power. All right, and all you have to do is just plug that in your calculator. All right, so this asks us to round to the nearest dollar, so I got 562.37, so to the nearest dollar, that would be $562. Okay, and then part C, I like to go through and box off or circle my answers so they really stand out. says using this equation, determine the year in which her stock will reach $1,000. So since we're looking for the year, we're looking for the x. The 1,000, the value of the stock, can go in for the y. So we'll have 1,000 equals, and we can just literally rewrite this entire right-hand side of the equation. So 379.92 times 1.04 to the x power. Okay, well, since the 1.04 is being raised to the x power, we need to get that by itself. So let's first start off by dividing both sides of the equation by 379.92. Okay, well, when you divide 1,000 by 379.92, you can either write that as, I guess, a number that's rounded to at least 4 decimal places, no less, because if you round too early in your problem, it throws off your final answer. I always like to keep it exact, so I'm going to actually just leave the left-hand side of my equation right now as 1,000 divided by 379.92. And I'm going to bring down the equals 1.04 to the x power. Now, the reason I just left it like that is because we know when our exponent is an x, and we can't get this to be the same base as this, we're just going to stick the word log in front of both sides of the equation. So we'll put a log on the left and a log on the right. Now, the reason we do that is because you're allowed to take the exponent and bring it to the front of the word log. So we'll have log of this ugly fraction equals x times log of 1.04. So now all we have to do to get the x by itself is just divide both sides by log of 1.04. All right, so that you guys are going to have to do in your calculator. And you wind up with x, I'm just going to put it over here because I'm out of room, x being equal to, I'm going to round for right now, 24.7. Okay, now it takes approximately 24.7 years for the value of her stock to reach $1,000. But the question says, using this equation, determine the year in which her stock will reach $1,000. So even though 24 normally rounds up to 25, her stock reaches $1,000 within that 24th year. So it's going to take 24 years past her initial investment. So I'm going to take the year in which she initially invested it, which is 2005, and I'm going to add on the 24 years, right, because it happens within that 24th year. Even though it's later on in the year, 0.7 of the way through the years, it's still in the 24th year, and we'll wind up getting 2029. Okay, so at this point, I'm going to have you go back and do number 3. And I'm also going to have you try out number 5 because that's another exponential regression. All right, so here are the calculator screenshots for number 3. You can see we plugged them into L1 and L2. We went to exponential regression. This is what we see. And then here is the format of our equation. So I just plugged in the A and B, and that's how I got my equation. When it says to round to the nearest 10,000th, that means 4 decimal places. And then part B wanted you to predict how many coins would be returned after the 8th trial. So we substituted the x, which is the trial, with an 8, and just plugged it in the calculator. And since you can't have a decimal of a coin, you round to the nearest whole number, which is 16 coins. Okay, so here's the answers to number 5. Now this time, I just took a screenshot of the final screen that shows the format of the equation, because we've seen this. It's the same thing over and over again. So in letter A, we get y equals 276.67 times 1.21 to the x power. Now in letter B, when we had to estimate the salary of a baseball player in the year 2005, well, according to the chart, it's the number of years since 1984. So I took 2005 and subtracted 1984 from it to give me 21 years. So 21 years later is what we're talking about. So I replaced the x in the equation with 21, and I just plugged that in the calculator. Now, when they say in the question to round to the nearest $1,000, keep in mind this chart is giving you numbers in thousands of dollars. So when they say 15,151, that doesn't mean dollars, that means thousands of dollars. So technically, that's really 15 million. It's almost as if there was an extra 3 zeros at the end. So to round to the nearest thousand, you can either stick the 3 zeros on the end and make it 15,151,000, or you can leave it as 15,151, but then you have to write the word thousand after it. And then in part C, you kind of have to apply the same concept. When they want to know when will the average salary be 3 million, well, since in the chart they're representing the average salary in thousands, you have to take off those last 3 zeros when you plug it into the equation. So you're really just plugging 3,000 into the formula. This time we're solving for x, so since our exponent is a variable, we're going to wind up having to use logs to solve. And we wind up with x being 12.5, approximately 12.5. So since it reaches that salary within the 12th year, I took 1984 and added on 12, and that brought me to 1996.